Alright, response video to Hothla Day and gravitational lensing. So, lots of the mechanisms of it. How do you see next to suns, the whole history of the experiments that demonstrate something, what our expectation of proof should be. It does get complicated, but there's two main issues, okay, where he's arguing that there's a significance or a meaning. The first is the focal length of a gravitational lens, and which gets, well, first let's do and the other is the seeing issue. And so he understands the scattering issue, but I don't think he fully understands what how gravitational lensing is done. So let's first just deal with that issue of the lens and what exactly is being argued. Now, in the Edinburgh, whatever his name is, experiment that proved Einstein correct, there wasn't a lens, like a whole lens in front of kind of thing, like the star was behind the lens and you saw something behind something. It's the edge of the lens that was the only part that was significant. And so it's like me just covering half of a lens. I mean, it still works. Well, with gravitational lensing, it's really just the very edge of the lens where the gravity is the heaviest. And then as you go further into the lens, it becomes less and less of a lens. So clearly the strongest part of the lens is the very edge of the lens. And so really all you're trying to do, you're not trying to get an image of something, you're just trying to distort the photons, deflect them. And so we're talking about a position change. So I guess if I was to draw a picture of it, the sun would be here, and all they were doing is there's a calculation of where a star would be without the sun there. So without the sun there, the star is at a certain position. With the sun next to the star, the position would be slightly different. So for a particular time of day, a particular second of the day, the star should have a certain position. And with the sun next to it, its position is different. So its position is out here instead of there, because of gravitational lensing. So what they're really doing is saying something, it could be as subtle as the star they're looking at should be there, and they're seeing it not even a full star's diameter in a different place. So they're just looking for the tiniest distortion. And the theory, so let's understand the theory. The theory doesn't have anything to do with mass. So if a photon was as big as the Earth, the same argument exists, that if I take the Earth and I move it 300 million meters a second, or 180,000 miles an hour, next to the surface of the sun, I'll get a certain deflection in the Earth's path. Now understand what that means, okay? So over a period of So if you're in gravity, on Earth it's 10 meters per second per second. On the sun it's only 70 meters per second per second. It seems like it should be a lot bigger, but it's not, because the sun isn't dense. So we're back to a density argument. So for something like the Earth at only 10 meters per second, you have to understand that the object going by is only going to be in the gravitational field for the thickness of the Earth first. So there's only 10 meter per second gravity at this one location. At this location it's much weaker. At this location it's much weaker by the inverse square rule, which means at twice the distance it's 1/4 the amount of gravity. So it's very weak till it gets to the middle, and then very weak leaving. So anything going through a gravitational field, depending on the orientation of the field, the size of it, the depth of it, it's going to be in it so brief a moment that there's only so much deflection that could possibly take place. So we're talking about, so you have to understand that over 300 million meters, in 1 second, there's only a change of 9 meters. Well, on the case of the sun, 70 meters. So 70 tiny meters out of 300 million. That's the difference in the unparalleled. So you're talking about an angle here of infinitesimally small deflection, just so incredibly small. So that's the context that has to be understood, that it's not the lensing in the full sense of the word, it's just the edge. So when they do illustrations of black holes, it's kind of funny because they illustrate the black hole moving, and they'll show it, everything around it swirling, everything getting diffracted, all the light from all the stars all around the black hole diffracting. And you don't need the whole lens to do that, you just need the leading edge, any edge. So he's arguing that the Hubble telescope can't look at the sun. Yes, it's correct. There's no point. If it looks at the sun, it's blind. The point is, it's looking right next to the sun. That's the whole point of the eclipse, was still to look at next to the sun. And not so close that, big giant flames are going to ruin your image. Obviously, they have to be far enough from the sun that they can still resolve an image. And certainly the Hubble telescope is more than technically capable of looking right next to the sun's corona. 200 miles away from the surface, 500 miles away from the surface, whatever the number would be. It can go any one of those numbers, and it will have a clearer and clearer image, obviously, the further away it goes, because it's not looking through radiation. So that's part of the problem here, is that gravitational bodies have atmospheres, and they're not necessarily atmospheres like ours of fluffy clouds, but they're atmospheres of radiation or flames or other ions that it's producing, and the sun certainly has an atmosphere of energetic particles, and the same kind of energetic particles that cause scattering on Earth will scatter light as it travels through that atmosphere. So you can't be confused. But that kind of diffraction should, theoretically, have the same probability of moving light up as it has moving light down. So your image should be distorted either way, which would indicate that what you're seeing isn't lensing but diffraction. But that, again, it's dependent on a premise that ionization doesn't create any alignment that tends to create diffraction in one direction. So now we're back to something like the two-slit experiment or something. So anyway, but the whole point is that it's established that it's theoretically possible. So by Einstein's figuring, a photon increased to the size of the Earth, passing by the sun at 300 meters per second, 300 meters per second, is going to incur enough of a gravitational influence to deflect its path sufficiently to be noticed. And that's the only part that matters here. So if we establish that as being the theoretical contention that was proven, I'm just saying clearly that theoretical contention that the sun lenses can be proven any moment. We can just follow the leading edge of the sun and see how many stars are out of position as the sun moves. We know their position when the sun moves to a different part of the field every day. So you just establish the position of a star at a particular time of day and just wait for the sun to go through that field. So on day 29, a certain segment of the field will be the one indicated. So you know where all the stars are supposed to be. You know exactly at what time it's supposed to be, where it's supposed to be. And you just see that when that leading edge of the sun hits it, whether that star is registered to be in the wrong position. And I'm just saying the fact that it hasn't been done, I think it's just an indication that they did it and they found they didn't get conclusive results. They didn't find what the expectation. It didn't meet that standard. And I'm just saying the focal length doesn't matter, because the advantage of something close is that it's bright, so you can see it. And there's a certain advantage to some things far away, but again, it really just has to do with how much it's being deflected. And ideally, being further away from the lens would give us an advantage, but the point I'm establishing is that it's already supposed to be, by the numbers, it's already supposed to be possible to see the difference. So we're already capable of seeing the angular difference. That's the contention. that it would be visible. So it really doesn't matter. It's really just about what you're looking at really doesn't matter. You'll either see a far away thing in a completely different position, or you'll see a nearby thing shifted, changed. But they're both detectable phenomenon is the point. And the point is that the Hubble telescope completely changed astronomy for that major reason. You could see during the day. You could see stuff that was near the sun. A whole side of the cosmos was now visible because you didn't have to wait until it was night and wait for the right angle. But I think, well, most importantly, you just didn't have the noise of the atmosphere, the distortion it creates. And one of the distortions is the fact that it would scatter light. Alright, so that's probably enough on that part of that argument. So I wanted to get to the time-sensitive nature of when you're in a gravitational field. And I've made this point about galaxies, and I want to stress it again, because he just keeps doing the same stuff everybody else does. Well, they didn't check because there's all this other evidence of lensing. But it's not rational evidence. It's not rationally consistent with their own physics. To see an image on both sides, that requires an incredible amount of diffraction. You're just guaranteeing that you have to have a focal length then. The point I was trying to make about focal length is it really doesn't matter the focal length on the edge. You're just trying to find distortion. You don't care about getting an image of something. And then clearly the lensing they don't have a focal length because they never have a clear image. They just have a bisected two images, which is just, like I said, the angular, the amount of gravity has to be immense from any focal length to create that much diffraction. And so they're saying it's basically, okay, so you have a galaxy as one of these flat things. Now my argument to you people is all the lensing images are like this. They're looking at the galaxy this way, and they see something getting diffracted. This is the weakest gravity, this angle. This is the strong gravity angle, because now you have the density thing. So now when something travels along this edge, it's in the gravity. You can kind of see it's in the gravity kind of a long time. Not only is it in the gravity for this whole arc, which could be very long, right? The galaxy is really immense. It has a huge circle. So it's in the gravity kind of a long time as it's doing this whole giant circumference, this whole piece of the circumference. And obviously there's some gravity coming in and some gravity going out. This angle, the gravity is thin. It lasts very short. In, out, in, out. It's there's very little time you're going to spend when you're going down this way, up and down across this thing. So the sides is where the strong gravity is, because you have to spend a long time in it, and it's stronger because the thickness of the gravity is thicker. I mean, people should be able to understand that simple premise. If I made this really big, you could sort of understand that if you came into the edge of it, you'd have really strong gravity, and if you came into the side of it, you'd have really, really weak gravity. So that's the truth of gravity. So I'm just saying it is kind of ironic, or no, it's problematic that I think almost exclusively all the supposed lensing images are of gravitational fields, of items in a gravity field that are flat to us. I don't think I've ever seen a lensed image on angle with two little, like I say, a little bright spot on one side. They do have galaxies that have little bright spots on either side, but obviously the bright spots don't go away, so they can't be lensing, because the thing behind them never moves and the galaxy somehow never moves, so that can't be true. So I'm just saying it's another piece of evidence that the evidence is poor, weak, I would argue irrational, because the moment of time, the amount of time in the strong gravity is so tiny this way, up and down. The only time you're in the gravity a long time is if you go across this whole edge, the length of the gravity. So again, but it's really, when they use lensing, it's probably not a great way to say it. I mean, we don't have another metaphor for what's happening, the diffraction. But it's like me making a lens like this, round lens, and just cutting the entire middle of the lens out and just say, screw that part. The only thing that matters is this edge. That's it. That's where all the lens is. And that's how gravity works. Gravity is strongest on the surface. The deeper I go into this thing, the weaker the gravity gets. The strongest gravity is right here where the maximum density, the smallest radius to density ratio exists. And that's on this surface. And so obviously if I take 4 of these little lenses and put them separated by space, I've completely weakened their density. And now if I make a circle encircling those 4 lenses, that lens will be a lot weaker than these individual surfaces. Alright, so I mean, I'm just saying, if Einstein was correct, and it's theoretically possible for the sun to lens light that we can see on Earth, as the experiment suggests, I'm just saying we have the technology now to see it all the time. To see stars move in their position every time the sun goes past the field. And it doesn't matter how far away they are. It doesn't matter how far the light source is away. The point is our position is fixed. And if they could see it in 1818, they should be able to see it now. It's the same exact angle. It's the same amount of diffraction. It's the same amount of... So if it was theoretically possible in 1918, it has to be theoretically possible now, and I'm just saying Hubble makes it something you can do every single day, every hour, every minute of every day. You can just look at the edge of the sun, have Hubble just go right ahead of the sun or right behind the sun, and watch the distortion happen. Right in the top edge or the bottom edge. Any edge of the sun will do. The distortion should be there, like a gravity well. The lens should be just thought of, the sun should just be thought of as a funnel, and the funnel on its edge is the deepest, so it's inverted. It doesn't get deeper in the middle, it's deepest on the edge. Okay, and the light's going to, bend on the surface and get distorted. There'll be distortion, not from its atmosphere, but from the light that's moving 300 million meters per second. 300 million meters per second is getting deflected by the less than, I don't know how many meters across the sun is, but it's nothing like 300 million. So the photon is in the presence of the strongest gravity for something like what, 1/100 of a millisecond, and then it's getting weaker and weaker. So I mean, it's in the actual strong gravity such a minute amount of time. But anyway, that's what the math says. I didn't say it. That's what they say. I say you can't bend a photon. I say that evidence is all over the place. The very fact that photons are traveling through billions of light years of space and don't get messed up substantially by all these gravitational pulls and tugs that have to be different over time, it's just evidence that quite obviously photons are not affected by gravity, just as photons aren't affected by photons. They kinetically pass through each other by the mechanism I have described. The simple, obvious, angular argument. I mean, I've drawn the X's. I've done the crap. It doesn't matter whether you think the thing went straight through or you think the thing got bent by 90 degrees. It's exactly you can't tell the difference. The universe will look exactly the same. One thing going one way, one thing going another way, and the frequency of the photon will be maintained. So photons could be constantly changing their identity. The point is that the thing heading towards us at a frequency can't be changed. You can't change the frequency. So I could keep interrupting something. Okay, so a photon's traveling on this line, and I keep banging into it kinetically, with the steel ball scenario. It wouldn't matter, because as this ball goes this way, this one's still going at the same frequency, will reach this location. It's not going to change its direction because its frequency will still be there, because it and the one behind it and the one behind it are going to do exactly the same thing. They're not going to be interrupted in their path. Like I said, it's a new billiard ball. If I made the one going white and I hit it with black ones, it wouldn't matter that, okay, yes, now the photon's black. It's going to be going the same way. The white one goes that way, right? I hit it with the black one, the white one goes that way, the black one now goes that way. So yeah, I've changed the color of it, but I didn't change its direction, its momentum, its speed. Nothing else about it has been changed whatsoever. It's still in a pattern that's moving at the same frequency, so I haven't changed it at all. And that's the fact of light. Light doesn't have any perpendicular dimension. It doesn't have an existence in the perpendicular. You can't affect it in the perpendicular. You can only terminate it. You can only have it enter a real gravitational well, a material gravitational well of an atom, and that's when its frequency can be destroyed, because that's when it continues in a direction and it's replaced by multiply different directions. It's replaced by a ball going this way or this way or this way or this way. And so the what's the right word? The pattern is interrupted. The ball is not only changed in its color, but when this happens, the thing released to do this is another ball in that direction. I don't want to get too complicated. I don't want to get into the kinetic argument, this lensing argument. But it is sort of important to why I don't think photons can be affected by gravity. Even though they have mass in one direction, the direction they're going. That's the whole, this argument I think is just so intuitive. I don't know why people can't get this. But it's the school of fish argument. When a piece of matter is sitting somewhere, it's sitting there because there's as much energy in it going this way as that way, as that way, as that way, as this perpendicular way. So all three dimensions are balanced in the sense that there's just as many fish, so to speak, moving in those directions. And that's what makes mass. So something like matter looks like it has mass because it has photons in it that are heading right for you. I possess energy inside of my matter, and that energy inside my matter is constantly going in all these directions. I mean, it obviously is contained in the sense that the directionality is exchanged, so it's only spending a certain moment of time moving in your direction, so to speak. It goes in your direction, and then it goes in the opposite direction, and it goes in this direction, and it goes in that direction. So no element continues to go in any one direction. It just spends a certain moment of every second moving in that direction. So it appears to have mass in that direction. So I'm like a laser beam that's only on for 1/1,000,000th of a second of every second. And then the next 1,000,000th of a second I'm going that way. And the next 1,000,000th of a second I'm going this way. So I appear to be something that has force because there's a certain percentage of time I'm heading right for you. But there's also a certain percentage of time I'm going exactly the opposite direction. And so that's what makes something appear to be material, is that it has energy in it going every single direction for some portion of its existence. I just think that can be understood, and that you can understand that if something is only going in one direction, that it can't have existence in any other direction. It doesn't have arrows in those directions. It can't possibly have a structure that could be tangible in those directions. I become invisible if nothing is moving in your direction, because then I'm going the speed of light in the opposite direction. You get it? Like, light can't even bounce off of me, so to speak. No, and light doesn't bounce, of course, but it can't bounce off of me because I'm moving the speed of light in the opposite direction. You can't possibly see me as matter. I become invisible if I'm moving the speed of light in the opposite direction. You can't see me. It just ties together so logically. And this explains inertia, momentum, time dilation, which is just cryogenics. It's all here, and it's all in discrete bits that can be accounted for. Quanta. And like I said, Einstein is correct to say the photon is element 1. It's the simplest element. He's just wrong not to realize that it can't have dimensionality in any dimension but the dimension it's traveling in. That it can't be material in any other dimension because it has no force in that dimension. It has force in one dimension. It has mass in one dimension. Matter has mass in many dimensions because its pieces of it are going in all of those dimensions or in all of those directions. And if there's any part of if the matter isn't producing anything in your direction, it means it has to be going very fast away from you, which means it's going to be very hard for you to see it. All right. Okay. And I'm just saying that this whole idea explains everything. It explains why, say if you understood the electron to be this balanced entity, ideally, when it's not moving, it's in a state where there's as much stuff going this way as that way, as this way as that way, as this way as that way. It's balanced. And then if I force it to move, it means without giving it more mass, without adding to it, it means I have to make this arrow bigger, the direction it's moving in. That means it has to spend more time going that way. More bits have to go that way. And less bits have to go these other ways, because those other ways are not in the right direction. And so it perfectly explains why EMF, or electromagnetic radiation, always leaves electrons perpendicular to their movement. They move this way, they expel the force this way, or up, or they expel the force in the other two perpendicular dimensions. And the reason why is now understandable. That if I'm a school of fish, and the school of fish is going to move, it means more of the existing fish in the school. Say if we can only have 1,000 fish in the school, you can't have any more. They all go the same speed. If those are the rules for the school to move, it means the fish going up, down, left, right, that kind of shit have to be converted. Some percentage of them have to be converted into fish going the way you want the school to move. The proportions have to change. And I've used the word imbalance over and over, but that's a key to this whole thing. Energy is only seeing in balance. The energy itself is everywhere. The only part you can detect is where there's imbalance, where there's an appearance of more going one way than another way. And it's not really that it's imbalanced, it's that it appears that way because the parts you can detect, or the part that matter is sensitive to, which is the polarization, is imbalanced. The quantum themselves are never imbalanced. It's only the amount filtered in a space that is imbalanced. So it's the polarization that's getting imbalanced. That's how it goes even a level deeper, than just being the little balls. It just really has to do with the orientation of them, the color. We just change the color. So the movement is an illusion of switching color. And you can sort of understand that. If I had I could have a whole table full of little cards that flipped color, and I can create the illusion of movement over that field by just switching the colors. Nothing really moves, their color just changes. That's pretty much the universe we're existing in. We're being fooled by it on 3 levels deep. Alright. Is it still working? It's getting kind of warm. Alright, so I think I made the point on the lensing. Again, they're arguing that there's enough of an angular change to see lensing with the sun. That's Einstein's argument. They found it, they said, so we can find it again. I'm just saying we now have the tools to find it easily. No problem. You don't need to do an eclipse. And that's just a fact. Not disputable. If it was there in 1818 or whatever, it should be there now, and we can see it by looking at almost anything that the sun passes the field of. Anything that the sun at some point in its orbit passes over that part of the cosmos, we should be able to see it lensed. Any photon at any distance. Like I said, ideally it'd be nice maybe if we had a lensed object that was 1 billion light years away and incredibly dense, because again, see, now we're back to a surface area. Having a lens further away is nice, because then it's less of an angle, but then it's much more unlikely that you're going to have gravity nearly strong enough, because it's going to be a tiny surface, just absolutely tiny by comparison to the amount of photons you need to deflect. You need to deflect almost the entire image of the object to have enough brightness to see anything, so you have to deflect all of the photons coming off of it, and if your lens is tiny, the image is going to be too big and I'm just going to see almost nothing. So theoretically, you get into trouble when you make your lens further away, unless you make a colossal lens, and making a colossal lens creates the problem where you have no evidence of strong gravity in colossal lenses. The outside of a galaxy does not have 70 meters per second gravity. It has 0.00007 meters per second gravity. That's not going to bend light. Alright, I think I've made the point. So anyway, I do want to, I'm going to play the Piro video eventually, you know, and I want to apologize where I indicated that Mr. Natural didn't come to my defense, because he eventually did. I'm not too sure I like his paraphrases, and you know, there's some, but you know, there's a lot of things I don't like. But he did make some salient, accurate representations of my position, and I appreciate that in defense of it. And I'll explain the other disagreements, you know, the context of any conversations that were supposed to happen with people, because I don't know anything about that. But anyway, yeah, the point is that I make arguments defending why I believe something. People keep claiming I'm just being dogmatic and I'm declaring it a truth and not explaining why it's a truth. I'm explaining why. And I'll again make a simple argument. People are talking about my lack of evidence and the lack of some kind of substance here. The substance is in the fact that this theory started off just doing gravity, and that every single piece of physics I tested it against, it came up with the answer. It explained inertia. It explained time dilation. It explains magnetism. It explains the perpendicular production of the forces of electricity and magnetism. Every time it's tested, it wins. Now, for me to create a fake theory, some sort of rubber band theory, whatever the theory would be, the fact that this theory hasn't failed to explain all of those things means that I would have to be you have to almost be more of a genius to come up with a lie that can do all of that than to come up with a truth that can do all of that. I'm no genius for recognizing the logically sensible progression of how this fits the puzzle pieces together better. It's better than bent space. It's better than time dimensions. There's no such thing as a time dimension. It's better than all of those things, and it goes all the way down to the core. From the core to the biggest parts of the universe, it explains every single motion. And does it in obeying the rules of conservation. You don't get to just make up as much gravity as you want. You don't get to make up forces. You don't get to convert matter into energy. You don't have to create dark energy or dark matter or dark anything. You don't have to do Huygens bullshit. But I'm just saying that the idea that I could create a fake theory that can pass a reasonable explanation test for all these other disciplines, all these other elements of the physical evidence, would make me an extraordinary genius. So, have it your way. I mean, if you want to call me a liar and a canarder and somebody who's making shit up, I've got to be one fucking genius at it to come up with a theory that can explain all these different elements of physical phenomenon that does in fact unify. You saying it's an illusion, it's a fake. Just saying how. I mean, I'm just saying the burden's on you. If you're going to say it doesn't do something, you have to explain how it doesn't do it. How it doesn't provide an explanation. Alright, so enough. Yeah, there's nothing to, you can't argue with, like I said, assholes. So I appreciate your video, Hoth, today. He always has all these points. I'm not going to say they're nitpicky, but I mean, your counter argument right here was just so typical of the crap I'm going to have to expect. Okay, I mean, I point out why Hubble can do the experiment. I point out it's the most famous experiment almost in history. It made Einstein. Einstein would be nothing without it. It proved Einstein right. It made him a high household word. This is kind of a substantially important experiment, and you're with credulity going to tell me the astronomers don't want to do, they have no interest because they've already proven lensing other ways, and they don't need to do any of this, and they don't need to prove any of this. This being the 100th anniversary of Einstein, which is even funnier, right? But yeah, we don't need to bother repeating the experiment, even though it's a fundamental part of what physics expects is repeatability. And instead, we're going to rely on a bunch of cosmological crap images that, again, they're easily picked apart, and most of them can only be salvaged by some sort of dark matter bullshit, some sort of God glue. There's no way they can fix them, because they don't make any logical sense. They're not consistent with physical facts. They're ludicrous physics. It's not just silly physics, it's ludicrous physics. And so if that's the expectation, that you're going to tell me that they don't need to bother, well, I think it's pretty significant. And but again, the real funny thing is this doesn't even mean anything. I mean, whether you establish the fact that you establish that light is a material thing doesn't really, and that you can bend it with gravity, doesn't really have a huge amount of significance to anything. The fact that it is an elemental element, that it has mass, is important. Whether that mass can be gravitationally influenced is not important, because it's such a tiny amount of gravity. Gravity gets so meaningless on the nuclear scale anyway, because the real game is the polarized gravity, which is magnetism and electricity, and we know that light couldn't give a shit about that crap. You can push magnets into light all you want forever, and you're not going to move it. Well, anyway, unless it hits an electron, which you can move with a magnet, because it's material. Even though it's not really thought of as matter, it's quite obviously very different than the photon. The photon is the elemental particle. The electron is a collection of them spinning, which is basically the definition of all matter. Matter is a collection of little things moving. It's not a particle. No element of matter is a particle, except for the fundamental particle, which is the photon, graviton, magneton, quanton. Alright, anyway, enough. So, I will do another video later. I just haven't finished watching the Puro thing, because I have to keep turning it off, because, you know, I just get so, it's so obnoxious to listen to these rude, arrogant, ignorant fuckers lie and get away with it. I hate liars that get away with it, and they're liars getting away with it. And that sucks. So anyway. Refute me if you can, fuckers. But you can't. Because I'm right about the physics. Till next time.